This is, as the title suggests, scatter plots, correlation, and regression lines. And that's what we have in front of us, a set of data with an x and y input, the independent variable versus the dependent variable. And then we plot them and we see a relationship and we put a line or a curve through it. So that's what this one is about. And here are these learning objectives, and this is directly from the OpenStax textbook. As you noticed, for this particular unit, I've used quite a number of physics examples because it's where I'm coming from. So here, one of the most powerful tools statistics gives us is the ability to explore relationships between two data sets containing quantitative values, and then use that relationship to make predictions. And here on learning objects, again, it talks about correlation coefficient, regression lines, and so on. Now, as I said, I've used physics, but that was for me to get you into this analysis of statistics. And then we're going to get outside of physics for the next unit and look at other things from more or less everyday life. I'm going to scroll a little bit down. I'm exploring the relationship, and I already mentioned this one here, the dependent variable and the independent variable. The independent variable is the one that you start with, and from that, the other variable depends on. Now I'm going to show you a couple of examples here very soon. Scroll a little bit down here, scatter plot, we already looked at that. And that's why this is scatter plot here, and here you have a curve that is aligned with it, trying to make the best one out of this here, and here possibly a straight line. Here that looks almost like a sine curve. It could be, for example, day length throughout the year. Let's see, I said again, I really tried to avoid that. This one is also kind of like a straight line, just a negative. And I just want to get to my other, this is almost a perfect line, and this is kind of why I did it with physics. I want to give you perfect data first and then branch out from there to, well, not so perfect data, but here we can see that we get a really good relation from, and then we have to see, well, what happens when we don't get such a good relationship, and analyze that. I'm looking for my other comments here. So there's one, strength and direction of linear relationship, and I'm also doing nonlinear relationships, that means curves. Can be also measured with statistics called the correlation coefficient, which I usually call R squared, actually. And I also use the words regression coefficient for that. So we look at that. And as I said, a few more comments here. Linear regression. So that's the line that you try to put through it, respectively, the curve, and then you have some kind of regression curve going through that. And what says here about least squares line? Well, yeah, which is what it is, but we're not going to do the math behind it. So if you look at this particular chapter here, and you find this about least squares and so on, and yeah, we're not going to do that. We're just going to use the results, which are the equations here. This here is our typical linear relationship, so we get a straight line of that, and I've showed you that several times. Y equals m times x plus b is what I called it instead. I know it's the y-intercept. It's usually called b in a math book. Here they call it y0, I guess. And then I altered that because some of the regression curves that we had were not straight lines. All right, let's see. I think there's one more comment coming up. Maybe that was it. Oh, that was it, actually. All right. So here is an overview of the words that I'm going to use. So there's the regression method of fitting a curve. Dependent variables. Here's, for example, a common relationship, the age and height of minors as kids are growing, and then through adolescence, the older they get, usually the taller they are, and you can plot that and see a relationship. Scatter plot, well, that's just plotting those. Regression coefficient, that would be usually the R squared. Again, it could be also called a correlation coefficient or coefficient of determination, or they're all related to each other. I usually call it a regression coefficient, and that tells us how well the data fit the regression model. And I will show you that in our case for the physics data, it was really, really good. Accuracy of data, well, how close a given set of measurements are to their true value. So for example, when we turn the air resistance off, all of a sudden we lost some I'm sorry, when we turned the air resistance on, we lost some accuracy of the data. Parameters, those are the numbers that we found in the regression equation in Desmos. Outliers, I will show them, some data points that differ significantly from other data, and we might have had a couple of those. And then I will also explain significant figures and trailing zeros. And that's all of this here just goes better with actually looking at the data that we analyzed. All right, so let's look at that. I'm going to open this Desmos here. These are some of the shapes that we encountered, and I really have to zoom in here so we can actually see them. There we go, that looks a little better. There we go, there we go. So over here I put these equations. Here's your typical y equals m times x plus 2, so that's a straight line. That's the violet one here. We did come across the parabola here. I'm sorry, square root. The next one is a parabola. We did come across the parabola as well. And then we also came across this exponential here in two different ways. Okay, so let's look at the original data. And these are mine. I looked at what students had handed in so far, and I think you're quite familiar with Desmos by now, and hopefully you noticed that it's really user-friendly. Let's see, I'm missing something here. All right, I found what I'm missing, so I'm just gonna close this down and open it actually again. So there we go. So I put some images in there, and that's what I was missing here for a moment. They're not essential, but there they are. That's the PHET that we used, the pendulum experiment. And so here, these data here where we have the length of the pendulum as the independent variable, and then here the y-axis, which is the time it takes to make one pendulum swing to one side and then coming all the way back to the other side, respectively from middle to left to right to middle again. That would be the dependent variable, and they're all looking really nice on the square root relationship. We tried first without the exponent n here. So I'm going to fix that one there. There we go. So here's a straight line, and it doesn't look too bad, but we can see, no, this is more like a curve. And the ones in the middle are above the line. The ones at the ends are below the line. So let's try a curve, and I told you what you do is you put a to the n power in there. There we go. And so we get this regression curve here, and it looks really good. And then this r squared value here, the regression or correlation coefficient, the closer it is to 1.0000, the better the data are, and we can see this is virtually perfect, which makes sense because this is a very accurate applet that someone wrote. These parameters that you see down here, once we look at these here, so the m is kind of around a 2, and I will tell you later it actually is a 2.005. Incidentally, it's not exactly 2. It is actually really a 2.005. This one, on the other hand, really is a 0.5. So it's roughly 2 or 2.005 times x to the 0.5 power. And I will show you that later as well. And this one here is so close to 0, it truly is actually 0. It's supposed to go through the origin down here, and that's why it says 0. I'm going to point out a couple other things. This one here, we can see that the accuracy for the period, of course, is very high. Apparently, they give us 5 significant figures, 1.2684. All of them are significant because that's what it measured. 1.0985. Even the 0 here that's sandwiched in there is significant. And this one here at the end as well, the 0.8970. By the way, this is 4 significant figures. The 0 in the front is just a placeholder. We don't even have to write it like this. We just write it there because of its looks. It just looks better. But the other one here is actually important because the timer really did measure that accurately, so we ought to leave it there. And the same thing happens over here. Again, the 0 in the front here, that's actually a placeholder. We don't necessarily have to write it, it's just there for looks. But the 0 in the back is actually important because if we don't write it, then it looks like, whoops, it looks like a rounded number. 0.1, 0.2, 0.3, but they're not. They're actually quite accurate. It's not just a rounded 0.1 meters or 10 centimeters. No, it really is pretty much exactly 10 or 20 or 30 centimeters, not a centimeter more or less. So even this kind of what is called a trailing zero, we have to pay attention to it at times. And this one, I know it looks odd, 1.00, but it is that accurate. The applet really used that accurate of a length for this particular experiment. All right, I'm going to go to the other one. I'll leave this one open here and let's see. Oh, there's the other one. There we go. So this is the second set of data where I told you to have it run through these large angles here, and I arbitrarily chose, respectively, I actually used a number generator to give me all kinds of angles, 76 degrees, 8 degrees, 26 degrees, and so on. Some of you actually just chose very large angle and came up with a line that's kind of like almost parallel to it, but it's a little bit deviating and still got very good data. I made a spread, that was the intention. And yeah, I came up with, well, the data are really not that accurate anymore because the original pendulum formula does not apply to very large angles. And so what we get here for the parameter in the front here, that's the M, it says 1.959, still pretty close to 2.0, but a little bit off, right? And especially the second one is off. The 0.596, you probably came up with something similar, yet somewhat of a different number, but it's definitely not around at 0.5 anymore. It's more like around at 0.6. And this one here still is relatively close to 0, by the way. So I wanted to show you here that when you alter things like that, you get actually, yeah, quite scattered data. All right, I'm gonna turn these off here for the time being without actually erasing them. We're gonna look at projectile motion. And there's that little plus sign. Notice that I put my data in the same table. So here's that one. And here it actually, sure, I'm going to go in there and change this one here to our independent variable was the velocity or speed in meters per second. That's how fast it shot out of the cannon. And then the dependent variable was the range, and it was measured in meters. The blue one here, I'm just going to leave that one on. There we go. These were the near perfect data, respectively. Actually shows your perfect data, right? The M here is a very small number, 0.0349. I will show you also later what that means. And then the N here really is actually rounded to, and that means x to the second power, which is x squared. And then again, the B actually really is a 0. And then someone can argue, well, why isn't the M a 0 here? Well, I'll show you later why that is. So these are the virtually perfect data. Now I'm going to turn on the ones with the air resistance and the different projectiles that we shot out of the cannon. And yeah, here we have a spread, and it still kind of follows more a curve than a line, am I right? So there it is. It's definitely not a square relationship anymore. It's more like a 2.7. It's almost like a cubic relationship. And that could truly actually happen then when you turn air resistance on and have these kinds of different projectiles, that changes quite a bit the regression equation. When you compare them, yeah, depending on how you shoot a projectile like that, it really depends on if you have the virtually perfect data with no air resistance, or if you have the, well, not so perfect data with air resistance. All right, here's the capacitors. So charging and discharging capacitor, that's the actual experiment that I did. So, and here, especially on the second one, the discharging one, I'm going to turn this one off. Here again, we see virtually perfect data. Notice this time around, oops, it's this one here. That one actually is really almost perfect data here, and this is an exponential curve. You have heard about these probably before. They go for radioactivity, for example, apparently also for discharging capacitors, which are integral parts to any kind of electronic circuits. You have plenty of them in your cell phone and your computer, these kind of tiny capacitors. In my case, they were a little bigger. And so we get a pretty good curve out of these here. I'm not going to explain in this case what the parameters are, well, except this one here. The M here is kind of the top voltage with which you started out, 2.69. For the other one, by the way, this one here, the 2.90 is actually kind of the battery voltage that we got. We had two AA batteries, and they ought to be 3.0, and I guess it was 2.9 volts actually. And notice this is also kind of an exponential curve, looks a little bit different, and it still approximates the data very well. Notice the R squared regression coefficient is 0.9997, so still very good, but not perfect. And if you look closely at the data, yeah, they're not exactly on a line, but we can be pretty sure, safe in saying that, yeah, this is the correct equation, the correct curve for these data. So what I just noticed is that actually I should plug some of these numbers in. I kind of almost forgot that. Pretty much forgot that. So here it is. Here's our regression curve. I'm going to add another equation to this one, another expression. So I'm going to take this one here. So the y equals 2.005, 2 if I want to, but that's okay, times, times x to the power, and now I'm going to use the 0.5 that it says there, and I'm going to leave out the b. We can see this black line here that is exactly the same as the regression curve, or here's just that one, and there we go. Now also, if I change this one here, I said that the 0.5 is actually the same as the square root. So when I type in SQRT for square root and then put the x underneath, there it is, exactly the same. So 0.5 from the laws of exponents, that is the square root as well. Okay, for the other one, so I'm going to go here, I'm going to skip the large angles because it's basically the same. So if I put this one here, put the expression in, and so I'm going to have y equals, going to look at the parameters. So the m is the 0.0349, there we go, times x to the, in this case it's around a 2, so x squared, there we go. Oh, I forgot to hit that little plus sign. And in any case, I think it's already there because the b is really small. I'm going to turn off, let's see, I think this one and this one. And then we can see that the red line is the same, the red curve square is the same as the blue one right there. All right, and then here is the pendulum, respectively starting out with the roots. So these are the roots, can also be defined as a special case of exponentiation. So when I take, this is from a Wikipedia page, I really like Wikipedia for math and physics because it's really accurate. So when I take the second root, or the square root, that is the same as writing 1 over 2 for the exponent, and 1 over 2 is 0.5, so that's where this one is coming from. Then the actual pendulum equation, that's what you would find, that's what I use in my physics class, is that the time for one swing, the period, equals 2 pi times the square root of the length over gravity. So when I take this a little apart here, just leave the L under the square root right here. Then I have 2 pi divided by the square root of g. So when I type that one in, I'm going to have 2 times pi, there it is, divide by the square root of, and in this experiment we used Alaska's gravity of 9.82. There we go, enter. And it is 2.005, just like the other one showed, so it looks like a rounded 2, but it's actually not. I'm actually going to fix this one here. Takes me a moment. There we go. Oh, I want to erase this one here, actually. There we go. And now I'm going to fix it. There we go. So this is actually 2.005 times the square root of the length, and that was the regression equation that we got. All right, for the projectile motion, this one here is for the range of a projectile without air resistance. Again, it's from physics, of course, so the distance or range is velocity squared times the sine of 2 times the angle divided again by g. Apparently it depends on gravity as well. Makes sense, both of those experiments. And when you plug this one in, the second part here, the sine 2 theta over g, I had you shoot those cannonballs or pumpkins or whatever at an angle of 80 degrees. And then divide by 9.82, you come up, or I come up with 0.0348, which matches the one that I got on there, the 0.0349. So this one really is the factor in front of it. Again, the b here is 0. And the last slide here is, for example, just for the discharging for capacitors. And again, this here would become like the peak voltage that you had there. And then this one here does have a meaning in front of it. It's kind of like there is no half-life attached to capacitors, but it's kind of like that it goes down to like half the value and so on. All right, so these 2 experiments here for dropping something for free fall. So here we dropped this Austrian astronaut, Felix Baumgartner, from an altitude of almost 40 kilometers, which is 25 miles, where he is so high that at first when he starts dropping, air resistance barely affects him. And so when we plot the data, I have to move this around a little bit. There you go. When we plot the data, we get a really almost perfect curve here, as he is in the first 20 seconds virtually not affected by the air resistance. This is actually his altitude data. Of course it goes down because he's losing altitude, and it is a square relationship because as he falls with time, the more time expires, the faster he gets, and he covers even more distance as he's still accelerating. And that's what you see here for the x squared. Here that's parabola, the square relationship, and the negative simply means that it's going down. Notice that the regression coefficient is virtually perfect, r equals 1. By the way, I should point this out. The 5.08 here is actually half of gravity, and notice it doesn't quite match the 9.82. So since this is half, when I multiply that by 2, I come up with 10.16, which is a little bit larger than 9.82. And this one here is actually his velocity data, also virtually perfect. Notice that we can see it's a little bit tiny off here, right? So r squared here is again 1, very, very good. This one is a straight line for the velocity data, and here actually we do come up with a really almost perfect 9.81 here. And again, the negative simply means that his velocity, as it's increasing actually downward, so it's a negative velocity that he acquires, hence that negative in there. Right, so that's when we drop him. Now when we drop an object, that's what I had you do, we get these kinds of results. And I'm just going to look at the graph, because looking at the graph is more instructive usually than looking at the table of data. So here we should come up with 9.82, which is really close to 10 here, so this should be our line here. But notice the big scatter that we have here. It should be a horizontal straight line across here. It's not, just like it says here, it should be 9.82. There we go, space there, it's all good. But it's all scattered all over the place, so as much as 20 or 15, as low as 8, and so on. And why is it in this case? Well, because it's a very inaccurate experiment that I had you do. I know at some point I gave my example data, and this is a real fluke here, statistical fluke, that I came up with a very, very good result. I was expecting I got like 15 or 8 or something like that. In any case, mine is not indicative of that I'm any better at this experiment. I think I just really lucked out. In any case, you see them scattered all over the place because we're dropping this, we're estimating the height, is it 2.2 meters, is it 2.1 meters, that kind of thing. And then we're trying to hit the start and the stop button as we drop it and as it hits the floor, and boy, that is so inaccurate. Hence, we get these really inaccurate data. And I want to point that out. That sometimes happens when you get data and you're trying to analyze them, and you have to pay attention to the accuracy or the inaccuracy that you got. All right, I think I'm finally done with this relatively long video for this assignment.